Hello friends, the topic for today is macrolides and we will start right away with the topic. Just hold on. Oh. So, uh, Abelardo Aguilar was a Filipino doctor and who helped Eli Lilly discover erythromycin. He isolated erythromycin from the soil samples. Unfortunately, never got paid for it. The general structure of erythromycin is a macrolide antibiotic. So the general structure of the macrolide antibiotic involves presence of a lactone ring. That lactone ring is encircled in blue over here. This is a 14 carbon lactone ring. It has 10 asymmetric centers and attached to it are two sugar molecules. The first sugar is called desosamine. Look at the amine function and it will be easier for you to remember this name desosamine. The second sugar is gladinose, which is marked in green over here. So, as I mentioned earlier, 14-membered lactone ring, 10 asymmetric centers. There are two sugar moieties, D-desosamine. You will remember it as DD. And the second sugar, first sugar is D, and so the second sugar is L. So D-desosamine and L-gladinose are the two sugars. So this is gladinose, and this sugar which contains an amine is desosamine. Okay, there are two semi-synthetic analogs of erythromycin. One is roxithromycin. The change is just at this carbon. Okay. And the second is azithromycin. Azithromycin has a CH2 over here. Okay. And instead of a carbon which is present here to which CH3 is attached, azithromycin has a nitrogen. Okay. I repeat, erythromycin has a carbonyl group here. Roxithromycin, this carbonyl group is converted to double bond N, and there is a further side chain to it. In azithromycin, that C double bond O is converted to CH2. But this CH3, which is present in erythromycin and roxithromycin, is converted to NCH3. This is a bioisosteric replacement. Going ahead, the mechanism of action of macrolides. I think you know how a peptide chain grows. There is tRNA. Attached to tRNA is an amino acid. 3 tRNAs join together and code for 3 tRNAs join together and start growing the peptide chain. Okay. And this is directed by mRNA. So this is the mechanism of action of peptide synthesis. 3 tRNA join at the site of action of mRNA. Look at the complementary base pairing between mRNA and tRNA. And this is the way the peptide chain grows. Now, what is done by macrolides? Macrolides bind to the 50S subunit of bacterial ribosomes. When they bind to the 50S subunit, macrolides block the translocation of peptidyl tRNA. Have a look at this. When this tRNA binds, this tRNA has to move. Unless this tRNA moves, this tRNA cannot bind. So this is called as translocation. This translocation of tRNA is inhibited by macrolides. But the most recent hypothesis suggests that all the macrolides stimulate dissociation of tRNA from the ribosomes during the elongation phase. Before the protein chain starts growing or the peptide chain starts growing, the tRNA is dissociated and therefore there is inhibition of protein synthesis. I repeat, they bind to 50S subunit. Upon binding, they block the translocation of peptidyl RNA and therefore block the protein synthesis. The most recent hypothesis states that it is not the translocation of tRNA that they block, but they stimulate dissociation of tRNA from the ribosomes and thus inhibit protein synthesis. Now, coming to degradation of erythromycin. This is a ketone which is amenable to acid catalyzed degradation. Okay, this is an ester, but this is a ketone which gets converted to a ketal. Now have a look at how a ketal is. This is C double bond O. There are two valencies. A ketal is this. So, a ketal formation takes place in acidic conditions, and this ketal formation is detrimental for the molecule. Now, what happens in roxithromycin? Just have a look at it. There is no ketal. There is no ketone itself. At this position, there is double bond N, and attached to it is oxygen. So it cannot form any ketal. This double bond will not be saturated by acid. And therefore, roxithromycin or even azithromycin, there is no double bond. And because there is no double bond, the ketal formation is not possible. Coming to metabolism of erythromycin. Shown here is desosamine sugar. And it is here that the main metabolism of erythromycin occurs. Erythromycin is acted upon by cytochrome P3A4 in the liver. Now what happens? Initially, N-demethylation takes place. This N-demethylation is followed by NOH formation. NOH formation is followed by further N-demethylation. Okay, this methyl group is gone now. And the resultant NO compound, the nitroso compound, attaches itself to cytochrome P3A4. If you remember the structure of cytochrome P, there is a porphyrin type of ring, and to it, the nitroso compound attaches. After attachment, macrolides inhibit cytochrome P3A4. Okay. Now, look what happens. The other drugs, which are metabolized by cytochrome P3A4, their metabolism reduces. And because their metabolism reduces, the circulating levels of some of the drugs increase. And these include theophylline, carbamazepine, cyclosporine, tacrolimus, warfarin, digoxin, terfenadine, astimizole, cisapride, lovastatin, triazolam, and disopyramide. So many drugs are metabolized by cytochrome 3A4. This is inhibited, and so the circulating levels of these drugs increase. Now, the troublesome part in this is theophylline, because theophylline has a very narrow therapeutic index. coming to the therapeutic uses. Mostly upper and lower respiratory tract infections are treated with macrolides, erythromycin, roxithromycin, or azithromycin. Erythromycin is 4 times a day, roxithromycin is twice a day, and azithromycin is once a day. So, the infections caused by gram-positive bacteria, mainly streptococci species, are treated with macrolides. And these drugs show a particular affinity for the tissue of respiratory tract. Therefore, their levels in the respiratory tract are more, and therefore their utility as upper and lower respiratory tract infection drugs is increased. So with this, we complete our lecture on macrolides. Next lecture we will see on chloramphenicol. Thank you.